Okay, so very good, very good. So today we will not have the guest lecture as I discussed in the email. So we will reschedule the lecture for Professor Doc Speroid. Okay, so I will keep you guys all updated. Our next, if it will not happen earlier, then our next guest lecture will be November 7th. Okay, November 7th by Professor Zhang Shan. She is an expert in the control and the simulation field in the MAE department. She is excellent. Yeah. Okay. So before today's class, I want to give an update of our current logistics so that everybody will be on the same page. Okay. So firstly, I have uploaded the homework number 2. You can start work on that now because we have talking about the trust structure. So this will be due end of October 31st. Okay. After that, we will post the solution. So make sure this you submit it on time. Okay. We said 12 p.m. but if you can send within this day, should be okay. Okay. So just make sure take advantage of this opportunity to practice the problem and then either form a group to study or do it individually. Make sure you have the hands-on skills to solve those problems. Okay. And we will have an exam number 2 on October 19th. This exam number 2, we will only examine the question, the concepts we discussed after exam number 1. So don't worry about the material before exam number 1. But those material we talked about, you should master it already. Okay, you should already master it, and you can do it by yourself without any problem. Okay, the basic concepts. So and we will reduce the problem number for exam number 2 so that we will definitely have sufficient time to complete within the class time, 50 minutes. Okay, so you can join on Zoom during the normal class time on October 19th, and then we will share the screen. Use the same format. You will see the exam sheet and do it and submit your solution. Okay, and our TA is great. He will score it and upload your score in the Canvas very quickly. Okay, so he is very efficient. So make sure that you guys use those good resources. Okay, I have a question. Kathleen, do you have a prediction of when we will get yes, very soon. Our TA already finished all the grading now. He showed me most of you did a very good job. So he will post it online. So you don't need to worry about it. Yeah. Kathleen, can you hear me?
Yes, thank you.
Sure. You are very welcome. Excellent question. Very good. So that's on the exam number 2. We may just give one question. Okay, one question that you can focus on in the exam. Yeah. Okay. I also posted a project, APCS project in the Canvas. So this will be due November 4th. We have already posted 3 videos. All of them are developed by Dr. Ting Dong. She is an excellent finite element teacher, and those videos are great. So we also posted 2 more videos you can watch in the class 10, October 28th, November 9th. You can watch those 2 videos. Those 2 are more advanced, but very useful, very helpful. Okay, you can use that, and then you start to work on the project. Use the APCS. I have forwarded you the link that you can download the APCS. You can use that, and I think that education version only allows 20 students to use simultaneously. So make sure you use it efficiently. Okay. If you have any question regarding to the APCS, you can contact our IT people in the department. They are the IT support. Austin is the team leader, excellent leader. So you can talk to Austin and talk to Debbie there to make sure that they can help you to solve any software issue. This should be minor, very straightforward. So just go ahead to follow the link and use Abacus. That's great. Okay, and then you see you can see my project. You can start to work on that now. Okay, and then submit it on the through the Canvas before this deadline. Okay, I saw a question from Mechania. The questions on the homework number 2 related to exam number 2. It's related because they will be the trust structure and the related concepts, but it will not be exactly the same. So it will be safe that you practice all the example questions we talked in the class, and then truly understand the materials we discussed in the class. Then you should have no problem in the exam. Okay, can you hear me? Mikani, can you hear me? Yes. Okay. Very good, Mechanic. Very good. Very good. Amanda, I have a question. Is there any way that it could be a video posted on how to install Abacus? The download. I see. We do not have that. We do not have the video to install Abacus. But I think that can be solved by you can call Austin directly in the IT office or stop by his office. He is a very nice person, very knowledgeable. So you can just install it in front of him. Amanda, you hear me? Amanda. Yes, Amanda. Good, very good. I saw your message. So you can go ahead to work with Austin to install the Abacus. If I think that has no issue, you can make it work. If many students have some problem to install Abacus, then you can talk to Amanda, because Amanda will get help from Austin. Then Amanda can write a few steps, procedures, SOP to guide the rest of the students. Okay, this should be very straightforward. So Amanda, you go ahead to install with the help of Austin, and then other students can consult you if necessary. Okay. Do you guys hear me? This will be an efficient way to use Austin's time. Okay. Yeah. You guys hear me? Amanda, you hear me? Sean. Okay. Good. Yeah. Very good. Very good. Thank you, Amanda, for raising this up. Yeah. Very good. Okay. So so that's all for current logistics about the homework 2, exam number 2, project, Abacus tutorials, and also about our guest lecture. Okay. So for the guest lecture by Jen Shang, the lecture will be on the Zoom. So we will not meet in the classroom, so that be very safe. Okay. Because recently the COVID patients number also increased. So let's be very safe, be very careful. I would love to stay in the classroom to talk with all of you, to give the lecture. But safety is our first priority, most important items. So then let's take the safe way to meet on the Zoom. Okay. So Dr. Jen Shang will also meet with us on the Zoom. So the link will be in the Canvas. Just follow that. Okay. Yeah. That's all the logistics that I want to share with you. If you have a question, just shout out or put it in the chat box. Okay. I think I have gone through all the questions in the chat box. If I miss anything, just shout out. Okay. I will answer it for you immediately here in the class during the class. Yeah. Very good. Very good. Excellent. Now. This is our schedule. Our schedule for the rest of the October. Okay, so we will make sure to follow it. But if something happens, like we have many questions in the class and we get delayed, or some other unexpected things come, we can adjust. That's no problem, and we will definitely keep the video recorded, and then you can review it after class. Okay, so to make sure everybody on the same page. So no worry about logistics. Everything should be in control. Everything is clear now. Okay. Very good. And some of you actually write me very constructive comments. It seems most of you are actually starting very well. They based on the survey and also based on your scores. The scores are all quite high, so that's good. That's good. So I'm glad that you guys are doing well. So keep up with your good work. We are now almost to the middle of the semester. Okay, so make sure that you follow the pace and learn well. Okay, you guys hear me? Do you guys hear me? Yeah. Okay. Very good. Very good. Sean, Corey. Very good. Very good. Okay. So let's start today's lecture. So in last lecture, we recorded a video and we talked about the plan trust element, right? So I hope you watched that video and then get the sense of how to convert that 1D uniaxial condition we have learned previously now to expand that concepts and then to know to be able to solve the problems in the non-uniaxial case, 2D case. Okay, so that is a trust structure. Okay, so we have discussed about how to convert from the local coordinate system to global coordinate system. So let's very briefly go through it, and then we will get into the new materials today. Okay, so trust structure, plan trust structure means in the 2D, mostly in 2D. Okay, so plan trust structure. So here, this is an example I have showed before. This is a 2D truss aluminum structure and a 3D truss structure. Okay, and then those structures are holding two parallel plates apart from each other, and then they can be used to sustain the blast loading on the architecture, and then they can absorb energy, and also they have the advantage of low weight. Okay, so save the material, and to effectively resist any coming deformation, any blast loading. Okay, so those structures can be used in many areas, like the satellite, the boat, ships, vehicles, and also the bridge, different architectures, bridges. Okay, so many buildings in addition to the bridge also use the truss structure, right? If you have visited Hong Kong, like there are many buildings, right? Many buildings, the bank that they are made of the truss structure, and then they're transparent. They use the glass in transparent glass in middle, and then those buildings are actually are very lightweight, but very strong in terms of the mechanics, and they can sustain earthquake, sustain the blast, high speed loading. So those are actually the engineering ideas that human developed to construct all those different structures. But in the nature, even without a human, in nature also native select the truss structure to sustain the life. Okay, so here I have shown you in the last lecture that a single cell, this is in the micrometer level, 10⁻⁶ meters level, single cell also generate truss structure inside of their body, right? So those are polymer, those green colored structure actually are polymers. Those polymers are holding the cell to stabilize their geometry, to maintain their homeostasis, to ensure the cells can sustain different mechanical stimulations, right? So that's why truss structure actually is everywhere. Okay, from human to the from the micro scale or molecular scale to micro scale to the macro scale, like human civil life, right? So how to better understand the truss structure, how to use finite element method to understand the mechanical state of the truss structure. What's the stress there? What's the strain there? What's the force displacement in the truss structure? Yeah, so that's actually the goal of our lecture. So there's some basic difference between 1D system we discussed and 2D system, the truss structure. Okay, so there's some difference you need to be very familiar with. Firstly, for the 2D system, they actually have a 2D, they are using a 2D element. 2D element. This element has 2 degrees of freedom. Okay, they can move either in the x direction and the y direction, 2 degrees of freedom or 2 displacement. Okay, 2 displacement. So they are not necessary only on one direction. However, this is in this case we are dealing with the bar structure, bar, right? Bar element, not a bin, bar element. Bar element, as we discussed previously, it is a very thin, very slender structure entity. Okay, so the force the bar are experiencing, by definition, the force is only around the axial direction. So when we talk about the 2 degrees of freedom here, we are not meaning that they will have for the single bar, if you look at it, it will experience a force in the y direction. We are not saying that. We are saying that for any single bar in this system, they are still experiencing, or they are subjected to axial force only. However, because they are connected together now, so they are not necessarily aligned with either x direction or y direction. So if you look at that in this coordinate system, x and y, this is called global coordinate system. Use the capital X, capital Y to denote it. In that system, when you look at it, any node there, actually the force can have 2 directions, x or y, and displacement also 2 directions, x and y. Okay, it's because that. But if you look at the individual one, the force is still around the axle. That is for the bar element. In the future, when we talk about a more realistic element, like a bin element, okay, then you will, the bin can sustain the y direction force and sustain torsion, okay, as a rotating torsion force, torch, okay. So that's different. That we will get there step by step. Okay. So here I just want to clarify the 2 degrees of freedom we are looking at actually is in the global coordinate system. Okay. In the local coordinate system, you still have only 1 degree of freedom. However, yes, and here is also, however, the stiffness can be applied only on the axial direction. That's what I actually, the extension of what I just explained. For the any bar element, stiffness is still around the axial directions, okay? Because it's very, very thin, right? So one important concept we need to know is a local coordinate system. So once you have a structure, you look at the structure, you actually are standing in the global coordinate system, okay? Now, if we stand on top of any individual bar, then we are in the local coordinate system, that is called LCS, local coordinate system. In that case, one dimension finite element formulation should still be used, okay? Should still be used. If a body fixed local coordinate system is constructed around the length of the element. In this case, we use the small x, small y to denote local coordinate system. Small x is around the bar, around the bar direction, axial direction. Y is perpendicular to that direction. Okay, they still follow the right hand principle. We discussed right hand principle. Okay, so and the global coordinate system is actually is chosen to represent the entire structure. You can have x in the horizontal direction, y in the vertical direction, or you can change it. You can change it to different rotation, different angle. But different angle will result in different relative angle between small x and capital X. That will determine the transformation matrix. So the final result will be the same. If you choose different coordinate system, final result is the same. It's just a different way to construct transformation matrix to solve the problem. Final results will be the same. Okay, so that's actually that's very objective. That's good. So and you can also choose local coordinate system in the way you want. So the x can go this direction or can go opposite direction. Either way is fine, okay? But when you choose different x direction, then the angle between local coordinate system and global coordinate system will change, and that will change the calculation process. But the final data, final results will be the same. Okay, so those are the important concepts, LCS and GCS. Okay, now for the local coordinate system, many cases, the convention is we actually not only use small characters to denote that, we also add the head bar there. Okay, so see U1 bar, small U1 bar, small U2 bar. This actually means displacement at the node number 1 in the local coordinate system. And because this is the bar element, we already know U1 is definitely around the axial direction, right? And the U2 bar, same thing. Local coordinate system, the displacement on the node number 2, right? And then F1x means the force around the x direction, axial direction in the local coordinate system on the node number 1. And then F2x bar is force on the node number 2. So in this case, we're actually standing on top of this single element. And then we construct this local coordinate system, small x, small y, and then using the same method we have used before. So we can construct this element matrix, right? So this is the same way we discussed in the previous lectures. Now, once we have this, our goal is to convert this equation to the global coordinate system. Okay, why we need to do that? The reason is this is a structure. It's not a. We need to know different elements, how they are, what are their individual mechanical state. Okay, but to do that, we need to combine them, assemble them into the global stiffness matrix and the structure stiffness matrix. But only by using the element structure in the local coordinate system, you cannot do that, because the local coordinate system for anyone, local coordinate system is different for any element. This one, x is around this direction, small x. For this one, element 2, the x around the vertical direction, right? So they have different coordinate system. Then the stress, not only stress, the displacement and the force obtained from the connective node will be different, because they are based on different coordinate system. So they're different. Then we will be in trouble. We cannot assemble them together directly, right? So we need to firstly write individual element matrix for each element, and then convert all of them into the global coordinate system. So they are all sharing the same global coordinate system. Then those element equations set can be assembled together to form the global stiffness matrix. Then we can solve the question using the same method, striking out the columns and striking out the rows, adding in the boundary conditions, and solve the unknowns, right? We can do the same thing. So now, because of this logic, then this element matrix formula, we will expand it. We will add the y degree of freedom. So the way to do it is we add the F1y bar, top bar, F2y, top bar, and then V1 bar, V2 bar. V means displacement around the y direction. Okay, so we expanded it to 4 by 4. Okay, 4 by 4. So then this is for one bar. Okay, one bar element. Each bar has 2 nodes. Each node has 2 degrees of freedom. So altogether 4 degrees of freedom, 4 force. So we will have this equation set. Okay, this is called 2D element equation. 2D element equation. Okay, and this is around within the local coordinate system, as we draw here, x bar, y bar. Okay, can you guys hear me? Yeah, very good. So this very basic. Okay, very simple. But many students need to practice it until they can master this. Okay, so that's why we go through it slowly. Now, once we have this equation set, once we have this equation set, we already know we can write it in the abbreviation way, right? Abbreviation manner. And then we have K bar. The top bar also means this is a local coordinate system. And this element matrix, element stiffness matrix has the following property. This is the same property we discussed previously, same property. Only difference is now is in the local coordinate system, okay? Now, within this local coordinate system, most important thing to consider is actually the angle. The angle between local coordinate system and the global coordinate system. For this one, because it's in a 2D, so this element rotate counterclockwise with the angle phi, and angle phi here, okay? So this is the angle. This phi, usually we consider cosine and sine of this phi. We use L equals to cosine phi, L. Use this letter to represent the cosine, directional cosine around the x direction, okay? And then M, this letter equals to sine phi. That is the cosine 90 degree minus phi, okay? That is the direction cosine around the y direction in the global coordinate system, okay? So this is the LM, and actually also has N. In the future, we also have N like a nose, N like a nose. N that will denote the direction cosine around the Z in a 3D, in the Z axis, okay? So just make sure you get familiar with this. Now, we have this element matrix now. Now we are going to convert it into global coordinate system. So in last lecture, we already discussed about it. We already discussed that if you have one coordinate system, U and V here, let me change to the point. Okay, we have U and V here, U and V. If the coordinate system rotate counterclockwise with the angle phi, it becomes a U bar and V bar. Then any displacement within the U bar, V bar, this new coordinate system can also be written in a way that they are in the original coordinate system, U and V. Okay, so these two can same element, same vector in one coordinate system can be also written in another coordinate system by using the correct relationship of angle here. So for the U1 bar, V1 bar, it can be represented in the U1, V1 system by multiply with this matrix, 2x2 matrix, cosine phi, sine phi, minus sine phi, cosine phi. So we have explained why in last lecture. We have using the chalk, we have drawn it on the slides, right? So you can go through that process, and then you will understand this important relationship. Okay. If you have another one, you can use the same way. Another one, U2, V2 is another vector 2. Okay, vector 2, you can use the same way. And then this vector 1 is actually displacement in the node number 1. It has 2 degrees of freedom in the global coordinate system, right? And then this second vector is the displacement in the node number 2 that can also be represented in the different ways. Okay, once we have this, we can combine this together to have the displacement in the local coordinate system in the right-hand side, and then displacement on the global coordinate system in the right-hand side, and then we put the matrix in. So this 2x2 matrix, non-zero matrix is here, right? First 2 columns, 2 rows. Second one, because they will be multiplied with U2, V2 only, but not U1, V1. So they will be on the column and the row 3 and 4, right? So then we can assemble this matrix. Other places is 0, but no multiplications, right? So we have this 4x4 matrix. This matrix is called a transformation matrix. And then we can write it Q bar equals TQ. So this is the important equation. And then we have discussed about yeah, we have discussed about the sum transformation can be used for the force because they are all vector transformation. So you can use the same way to convert global to local and local to global. And that's why this T is important. This transformation matrix T is important. And this T actually has some very unique properties. Its inverse equal, the inverse of it equals to the transpose of it. So in this case, then F bar equal to T times F. Also, we can multiply inverse from both sides. And then the F bar times T inverse equals to F. And then we can rewrite it, F equals to T inverse times F bar. And then T inverse equals T transpose. So that means that F equals to T transpose times F bar, right? So, and so that you can see by transpose these two, you can transpose this transformation matrix, you can convert degree of freedom or force from global coordinate system to local coordinate system or vice versa, just by transpose the transformation matrix. That's the beautiful part. Okay, so it's a very systematic. And then for any matrix that has this kind of property, its inverse equal to its transpose. That kind of matrix is called an orthogonal matrix. It's called orthogonal matrix. What it means is any components, any columns there, you multiply, you dot product those columns together, they will equal to 0. Means any columns here actually perpendicular to any other columns, or any rows here are perpendicular to any other rows. It's the same thing. Here you see this row cosine sine 0 0. If it dot product with the second row minus sine phi cosine phi 0 0, then this multiply together minus sine phi cosine phi, and then plus sine phi cross phi cosine phi equal to 0, and then 0 0 equal to 0, right? Same thing for the columns. If you multiply each one, any select the two together, they equal to 0. So all those are different multi-dimensional matrix. They are actually different base, different axes. They are perpendicular to each other. Okay, so those kind of matrix is called orthogonal matrix. These are very, very useful. When you solve the eigenvalue problem previously, you actually construct an orthogonal matrix. All the eigenvectors, they actually construct the orthogonal matrix together. Okay, because they are mutually perpendicular to each other. So with this, we can start to look into the bar the bar structure we just discussed, right? So let's first use the algebraic representation, and then we can quantitatively add in the numbers. Now, for the two bar we just mentioned, one is this has an angle phi with the horizontal direction. Another one is perpendicular to the horizontal ground, right? So for the number one, we actually have an angle c phi here. If we look angle phi, which is the angle between local and the global coordinate systems. Now, we first write the local coordinate system, the element equation. That is this way. So we have a f1x, f1y, f2x, f2y here because this is the bar element. So we only have a x, right? X direction, non-zero. Y direction all 0 because now you are standing on top of this bar, right? So the Y direction is actually not around the axial direction. So that's why they don't have non-zero components. So that's equal to 0. So then we have this matrix constructed. You see only the X components related are non-zero X components because it's number 1 and number 3, right? Now from here we can write an abbreviation for, and then we will convert this into the global coordinate system. The way to convert is we already know F bar equals to TF, Q bar equals to TQ. This is the same. And then we times the T inverse from both sides. On the left hand side, T inverse times this equal to F. So then you only have the global coordinate, global components left there. And then T inverse times K bar times T is a new matrix, right? Matrix times matrix times matrix. This is a new matrix consisting of the product of 3 matrices. That one we write as K, directly write as K. Okay, we in a small character because this is the element matrix. So with small character. Now this K equals T minus K bar times K, or T minus is actually T transpose. It's the same thing. Okay. Now we already know what is T. We already know, right? We already know K bar. K bar is this one. K bar is this one. T we already know. Here, this is the T. This is the T. Can you guys see my screen? Yes, excellent. So we know T. Now, then we can calculate what is K. So we will find out after the calculation, you can practice it. After you adding the number in, you will get this K. Okay. This K, remember, this K contains both matrix component as well as the material properties here, because this is the bar element. We have EA divided by L. And make sure when you do the homework and do the exam problem, make sure those numbers are all included there. Okay, so this is important. Here, EA is the axial rigidity. Okay, and then this matrix has some important properties here we discussed the last time. Now, once we have this, then based on the question, based on the data provided in the question, you can start to add the quantitative number in, like the material property and the geometry properties. So here you can see in the problem, they usually give you the diameter, Young's modulus, and diameter gives you the A area. Young's modulus is what you can use directly. Okay, and then dimension also given for these 2 elements. One is 8 centimeter high and then 12 millimeter wide. Okay, and then from here, from these 2, you know the angle now. You know the angle theta, and then from theta, you can convert the local coordinate system around the element 1 into its global representation. Okay, so for the element number 1, you first write the connectivity. You write the N1, N2, and N3. So in this way, if you write N1, N2 in this way, then the angle is here, arctangent 8 divided by 12. If you like to select in another way, N1 here, N2 here, then the angle will be different, right? So angle will be from this line up to with respect to the horizontal. So it's larger than 180 degree. It's also fine. You can also do it that way. Then the theta will be different. Then the calculation will be different. The final results will be the same. Okay. So we actually, to keep it consistent, we recommend you to do it from left to right to denote different node number, as we did in the 1D spring system, right? So then it will be very difficult to make mistakes. So then we can, from based on this, we can construct a local coordinate system. First, they construct the element matrix. Okay, and then from here you can write expanded to 2 degrees of freedom for each node, and then from here you can calculate the element stiffness matrix in the global coordinate system, which is like this. Okay, and then you can add the number given in the problem into the equations. You will have these numbers in. Okay, from those numbers, we already we can hold it here first, and then this is in the global coordinate system. Then let's go directly to repeat the same process for the element number 2, and then get the representation in the global coordinate system, and then 2 equations can be assembled together. Okay, so for element number 2, you have this way. You have N2 here, N3 here, following the direction N2 to N3. You have this direction, horizontal direction, point downwards. The angle of this x-axis with respect to a global coordinate system is here, minus 90 degrees C, minus 90 degree. Okay, minus 90 degree. Then you can construct a local coordinate system element matrix, and then you add the 90 degree that angle in, following this equation, you can get the K for the second element. Okay. For second element, you can calculate that. And then you can add that together, which actually is this one. You will have this number, the second element, after you're adding the sine, cosine, phi equal 90 degrees. Okay. Then you can combine two element matrix together. The only overlapped part will be the U2, V2 location, because that is the node number 2. The two elements actually combined together. And then here, when we combine together, still remain the displacement unchanged because that's shared by different elements. And then add the force together. And then once force is added together, we know that based on the force equilibrium, all those those internal F force added together equal to the external force. So then we can write it as the external force, capital F 2x, capital F 2y, right? And then based on that boundary condition, on the number 2, actually we have F2x equal to 50, F2y equal to 0, right? External force. So then we have the boundary condition that for the node number 2, we have the force boundary condition. Displacement is to be solved. For the node number 1 and node number 3, displacement are fixed, no displacement, and the force are unknown. Force are to be resolved. Then we can apply those boundary conditions into the equation. Okay, so you can see that here unknown force are listed, unknown displacement are listed. Okay, and then all the element in the matrix already can be converted into the quantitative data. Okay, now from here we can, following the same method we learned before, we struck out the rows that corresponding to the unknown in one side, and then put all the unknown in another side that contains the matrix information. Okay, so in this way, computer actually, the way to do this is because computer can solve those matrix easily. They can quickly multiply the inverse of this matrix to one side, and then to both sides, and then solve those unknowns. The computer is more suitable to calculate those kind of equations. Okay, you can use MATLAB to solve this. Now from here, then we can get the U2 V2 because we have two unknowns and the two equations here. So U2 V2 here is resolved, and then we can put that U2 V2 in. We can directly solve the force, reaction force on the two nodes hooked to the ground, F1 and F3. Once we put those numbers in, we can calculate F1, this number, F2, this number, right? So here you see F2, F1, and F3. And you see F3 have a 0 number here. Why? That actually is the very good sign because the F3 is on the node number 3. That element 2 on the node number 3 is the vertical direction. So the force around the x direction equal to 0. So this number actually tells you your calculation is correct. Okay, so we have a force calculated. And the reaction force, you can see reaction force is parallel to the element length, because they are around the x direction. Okay, so overall, we will have a global force, global displacement all solved up to now based on the equation we use. Now we can look into the local coordinate system, look into the local part. So we already know, using the transformation matrix, we can convert displacement from global coordinate system into local coordinate system. We already know that. We just discussed about it. Now you put this number in. You now know the global displacement, U2, V2. Global displacement in the node 1, all 0, because this is an anchor there. Then by multiply this 2×4 matrix with the 4×1 matrix, you get a 2×1 vector. So then that the 2×1 is actually the displacement in the local coordinate system for the element number 1 that has node number 1, node number 2. Okay, and then once you know displacement, then we also know the material properties of that element, right? Then we can add that displacement in to the element matrix, element stiffness matrix, then we can directly calculate the force there. Force applied to the two nodes, node number 1, node number 2. In the local coordinate system, we'll find a force equal to minus 6.2 and positive 6.2. That's accurate because these two numbers should be in equilibrium, right? So in two nodes, right, by itself, then this is in the equilibrium part. So you can see there's no force component in the local y coordinate system, in the local y direction, right? And in the x direction, the two forces are equal and opposite, okay? And the force in the second node is equal to the element force. That's by convention. In the second element, the force is the element force. And once we know the force here, we can also calculate the stress. Stress is the force divided by the area. We know the diameter, so we know the area. So when we calculate it, we get the stress there. Okay. So then we will get the complete information in the system. From here, the element force is calculated by the displacement change, right? Using the Hooke's law, we can calculate that. And then this is in the local coordinate system, okay? Because we use the UJ, UI with bar, local coordinate system. We can calculate those element force. And then this element force can also be viewed in the global coordinate system. The way to view it is we calculate the force using the global displacement. So, but the number will be the same. Force is still there. They still around the actual direction of the bar. It's just a different way to calculate it. If you just directly use the displacement in the local coordinate system, very straightforward. You will use the two displacement, calculate it. But if you don't want to use that, if you want to use the global displacement you measured, that's also fine. You just need to convert global displacement UJ, VJ into the local coordinate system by multiply with the direction cosine. Then this actually is the same one we discussed during the transformation matrix. So from here, UJ bar equal to LUJ plus MVJ. UI bar equal to LUI plus MVJ. So that's L and M actually is the cosine sign in the transformation matrix, same way. So once you know the transformation matrix, you can measure displacement in the global coordinate system, both around X and Y direction. And then put that into this relationship. Then you can calculate the global force, the element force. You will get the same results. Okay, so here here is one example. You can give it a test. This is the element and the displacement and the material property and the node connectivity all have been listed here. When you do the homework and do the exam problem, I suggest you to follow this using the same style of table. Write down all those things correctly. Okay, different angle between the element and the global coordinate system, and the corresponding L, M, you all write down. Once you assemble this table, then following the method we discussed, you can solve any different truss structure. Okay, so that's all for and here is one more example here you can use it to resolve. Now you are able to solve those 2D structure now. Find out their individual mechanical state. That is excellent. So you can do those examples now. Okay. Next lecture we will start to talk about the 3D structure. Okay, 3D structure. There's this kind of architecture uses 3D structure, but the principle is the same. Okay. Okay. I will see you guys Friday then. Yeah. Thank you. Very good. Very good.